Now let's do a couple more examples looking at the central limit theorem.
Awesome, can't wait.
So I have two examples here, and I'm going to have Wade go ahead and guess what his answer is.
So Carly kept me completely blind. I have no idea what's going on here.
Yes, and I'll give you a hint. It's about gambling.
Ooh.
So
I like being casino owners. So.
Yes, you do. So this says to look at the following situations below and decide which you think is more probable and why. So also, as you're watching this video, it might be fun to actually record your guess as well. So as I read these two, think about which one do you think is more probable. So there is situation number one. It says you play roulette 100 times, betting on red each time. What is the chance you win more than $1? So play roulette 100 times. What's the chance you win more than $1? That's scenario number one.
Okay.
Scenario number two says you play roulette 900 times, betting $1 on red each time. What's the chance you win more than $1? So same scenario, except you're playing 900 times instead of 100.
So as a casino owner, I know the people who are in the casino a lot keeps losing more money. So I think it's probably going to be just 100 or...
Which is more probable?
More probable. I think you're probably more likely to come out ahead if you stop early.
Ooh, okay. So Wade thinks if you play 100 times, that situation is more probable.
Though you're going to win more often if you play, or win more times if you play 900 times. But I think it's going to be slightly less often. This is tricky. This is a good problem, Carly.
Yeah, we're going to do the math to figure this out. A lot of times when I ask students this question, they say, well, the more you play, the more likely you are to win. And so they're like, if you just sit there playing over and over again, you'll win more. So we can test it out. Is that the case? And we can use the math that we know about expected value, the central limit theorem, and distributions to solve this question. And then you can go to the casino. So you play roulette 100 times, betting $1 on red. What's the chance you win more than $1? So because we're playing roulette 100 times, we know that the central limit theorem is going to kick in and that the probability histogram is probably going to look close to the normal curve. So basically what I have to do here is convert $1, that's the value that I'm interested in, to a z-score, and then I can find the area above it to figure out the chance we win more than $1. Does that sound good?
Sounds great.
All right, so I'm going to use the standard normal curve. $1 is in dollars, so let's convert it to a z-score. So step one is to convert to z-scores. I want to take my value minus the expected value divided by the standard error. So my value is $1. Ooh, and I don't have my expected value in standard error here.
Looks like we need to do some calculations.
Looks like we need to do some calculations. So this is actually, I am going to model this just as a regular discrete random variable, because actually with roulette, we're interested in your winnings. And if you win $1, but you don't just not get any money. If you lose, you actually lose $1. So if I was going to find really quick my expected value, I am going to just take the sum of X, my outcomes, times their probability. So for winnings, I can either win $1, right? So that would be $1. And the probability of winning, I win if I get a red, and there's 18 reds. So that's 18 out of 38. Plus, I could lose $1, -1. And the probability of that is actually more. It is 20 out of 38, because I lose $1 if I get a black or a green. There's 18 black and 2 greens. And we're playing 100 times, so I want to make sure to multiply that by 100.
And then what I get when I do that calculation, I get -5.26.
Okay, so I have, my expected value is -5.26. So that's not great, right? I have a negative expected value.
Ooh, that seems like I'm gonna be losing some money.
Yeah, so this is saying if I play roulette 100 times, I'm expected to lose about $5. And then the standard error, again, this is just a regular discrete random variable. To find the standard error, I am going to use the formula for standard error, which basically says you're going to take the value, so $1 minus the expected value, -5.26, square it and multiply it by the probability, 18 out of 38, plus we have my second value, which is -1, minus my expected value of -5.26, square it and multiply it by the probability, which is 20 over 38. So these are just the formulas for discrete random variables, the expected value, and standard error. And again, I'm going to multiply this by 100 just because I want to be in dollars. So Wade, what do I get?
You get 10.
10 looks about right. So the standard error is about $10. So $10. And when I convert to standard units, what do I get, Wade, as my z-score?
So if you convert this to a z-score, you do the value minus expected value over the standard error, and I get 0.63.
0.63. So I'm going to mark that on my standard normal curve. Here is 0.63. And then when I draw my picture, I want to know what's the probability I win more than $1. So $1 is 0.63 standard errors above what I would expect. And remember, I would expect to lose $5.26. And then if I'm at 0.63, that is where $1 is on this curve. So now for my final step, I can figure out this probability. And Wade, what do you think would be the best way to do this? This isn't a CDF. Instead, it's like the opposite of the CDF.
Yeah, it's the other side of the curve. So I would have to do 1 minus the CDF is how I would approach this.
That sounds great. 1 minus norm.cdf of 0.63. And that will give us the probability of winning more than $1 if we play roulette 100 times betting on red.
So 1 minus norm.cdf of 0.63 is 0.2643.
0.2643, or 26.43%.
So if I play roulette 100 times, according to the normal approximation, I'm going to win a little, just win $1. Just walk out a little richer than I walked in, only 26% of the time.
Well, win more than $1, but yes. So that's not that great, right?
Not really.
Let's go ahead and calculate this for situation 2. And for situation 2, just because it takes kind of long to calculate the expected value and standard error, Wade, I'm just going to have you go ahead and give them to me. So the only thing that changes is we're playing 900 times instead of 100 times. So everything I did in situation 1, wherever there's a 100, I am just going to multiply that by, I'm going to use 900 instead.
So for 900 games, the expected value is negative $47.37.
Right. So we have, there we go, negative 47 point.
Negative 47.37.
0.37. And then what about my standard error?
Your standard error is exactly 30.
My standard error is exactly $30. So we have our expected value of negative $47.37 and our standard error of $30.
That's what I calculated.
Perfect. So our z-score for $1 is going to change, right? Because my expected value and standard error both changed. So I have my value minus expected value over standard error. So Wade, if you can do this calculation for me, I have $1 minus negative $47.37 divided by $30.
Yeah, so that's 48.37 over 30, or 1.61.
1.61. So when I draw my picture, if I'm playing roulette 900 times, winning more than $1 is actually over here. It's a little farther over at 1.61. So 0, now my expected value is actually negative $47.37, and $1 is way over here. So I again want to know what's the probability of winning more than $1. So I can do the exact same thing. I can do 1 minus norm.cdf, except now instead of 0.63, I'm going to use 1.61.
So 1 minus norm.cdf of 1.61 is 0.05369, or 0.537.
Wow. So this probability is actually about 5.4%.
Exactly. That's really low.
That's really low. You should not play roulette 900 times. So Wade, you were right.
Yeah, I know as a casino owner that when people walk into the casino and they just gamble all day, they leave with nothing.
Exactly. So these both situations had negative expected values. And actually, if that's the case, the more you play, the more likely you are to lose. So this might go against what you originally thought. So it's always good to double check with the math. And then the very last thing I want to talk about today is something called the continuity correction. And in some cases, it's necessary to actually make the normal approximation more exact by moving the endpoints of an interval to the nearest half integer. And we call this making a continuity correction. So this is because the normal approximation is a continuous distribution. So if we ask the question in 100 coin tosses, what's the chance of getting exactly 50 heads? Well, if I think about the normal approximation, that would technically be the area of getting exactly 50 heads would just be the area of a line, which is technically 0. But we know 50 heads is what we're supposed to get. The probability isn't 0. So oftentimes what we'll do is actually find the area between getting 49.5 and 50.1 heads, or sorry, 50.5 heads to give this a little bit of area. And we do the exact same thing we did up here by converting both of these values to z-scores and finding the area in between. But it's important to note that the continuity correction, if you're using the normal approximation for a discrete random variable, is super helpful. And I think that is it for the central limit theorem. Hopefully you enjoyed nerding out with some casino problems and know a little bit more about how to calculate what you're going to win when you're gambling.